Hello, my name is Radoslav, and today I'm going to present and give a practical example to my bachelor thesis on the topic of feature-based deployment of IoT applications in MontiThings. The goal of this thesis was to solve the problem of software variability in IoT applications by integrating existing software projects together and providing a feature-based approach to managing and deploying IoT applications. The first of these existing software projects is called MontiThings. Built with Monticore, it offers a way for developers to specify IoT components and their behaviors, and then deploy these components to real IoT hardware devices. The main entity in MontiThings is a component and connector diagram, which specifies the structure of components and how they interact with each other. In front of you is a practical example of a smart home test case. As you can see, there is this main smart home component, which contains a number of subcomponents connected together using ports and connectors. These connectors pass around some information, which is necessary for the proper operation of the components. The MontiThings project is combined with the feature diagram language project, which offers a Monticore-based textual representation of the popular feature diagram paradigm. As feature diagrams are especially useful for managing software variability, they are an appropriate approach to solving the software variability problem at hand. Continuing with the smart home example, this is a feature-based representation of it. As you can see, we have the main smart home feature here, which consists of a number of sub-features. These features can be mandatory, optional, or even connected together with OR and XOR group. There are also some cross-tree constraints here. To provide a meaningful way to interact with the product of this thesis, an existing graphical interface has been utilized in the form of the MontiGem IoT deployment application. MontiGem works by supplying backend and frontend handwritten files and running them through to the proprietary generator, which then outputs the functional application. The figure in front of you gives the architecture overview of this thesis. We have the previously mentioned existing tools together with the newly developed tagging tool. This is the main entity that provides the connection and interaction between both MontiThings and the feature diagram language. The tagging tool utilizes the tagging language, which is where the binding of the project happens. This figure visualizes how that binding exactly occurs. On the left, we have a tagging body containing a number of tags. Each tag starts with the keyword feature, followed by a feature name, followed by the contains keyword, and then an arbitrary number of component instances. Having defined the language, we can also define the tagging model of the smart home test case, which is what this figure represents. We have the main tagging body, a number of tags, and each tag consists of binds a single feature to a number of MontiThings components. Now I would like to show a practical example of operating with the tools. We start by providing two files to the IoT deployment application, a deployment info.json file generated by MontiThings to access the configurations page, and an archive containing all relevant model files like MontiThings components, the feature diagram model, and also the tagging model. It is important to keep the package structure intact, which is why the outermost folder of the project is archived. The next step is to start the necessary components, and in particular the tagging tool server, which manages the requests from the IoT deployment application. After that, we can log into the application itself and import the previously mentioned JSON file to access the deployment configuration page. This page has been extended with a new subpage exclusively dealing with feature configurations. Now we can import the archive and see the table being populated with different features. These features can be selected, which effectively builds a feature configuration. After the selection has been made, we can verify it against the feature diagram. It can be validated against the feature diagram and even completed to a valid one if the user requires it. In some cases, it is not possible to validate this feature diagram to complete it to a valid one. and the tool makes sure to inform the user of that outcome. We can also determine maximal configurations together with maximal deployable configurations. The difference here is that the former tries to find out the maximal valid configuration with regards to the feature diagram, while the latter also tries to deploy said configurations to the existing IoT infrastructure, effectively filtering out undeployable configurations. Here you can see the outcome of the maximum configurations button, displaying 6 possible configurations that the user can choose from. The selected features also have an effect on this analysis because selecting some feature means only configurations with that feature present should be displayed to the user. And as an example, we can now select the small fridge feature, which narrows down the selection to only 2 configurations, both of which have the small fridge, contain the small fridge. When the user likes a particular configuration, they can select it, and which is reflected here in the table, and at the end try to validate and eventually deploy the whole deployment configuration. This functionality was already present in the application and remains largely unchanged. With this, I conclude my practical example and also this video. Thank you for your attention.